Good afternoon and welcome once again to our Friday afternoon security seminar. This afternoon I'm very happy to introduce our guest. When I got started in the field of information security many years ago, there were a number of people whose names I kept coming across. And I was thinking about, wow, these people have done some great work and I look forward to meeting them someday, except I was a little bit worried about actually running into them in person, figuring that as senior people in the field they might be very intimidating. And it turned out that after meeting them, they weren't so intimidating after all. In fact, they were quite nice and very helpful of junior people in the field and very interested in what was going on. Our speaker today is one of those people who has been involved in information security for a very long time. He's spent 22 years at the Naval Research Laboratories, where he's very well known for work in a number of areas relating to information security. Recently, he has gone from Naval Research Labs to MITRE Corporation, where he continues to work on information security. He has a connection to Purdue, having taught here for 1 year in the mid-1970s. And he's back visiting us to give us a presentation on architecture and components for information security. And so please join me in welcoming one of the real leaders in the field, Dr. Carl Landwehr. Carl, thank you.
Thank you very much, Gene. It's always a pleasure to come back to West Lafayette and see what's changed and what hasn't. What I want to talk about today, the title of the talk, actually, I think I'm going to apologize a little bit because it seems to me a very dry-sounding title when I look at it. And actually, originally this title had a different talk. This talk had a different title, which was called Gadgets and Cheap Tricks for Multi-Level Security. But I found that when I was giving this talk to audiences of people that we were hoping were going to fund it, they didn't really want to fund gadgets and cheap tricks. They wanted to fund architectures and components. So the title changed. Multi-level security, which is really the domain that this work that is primarily addressed to, that I'll be talking about, it has requirements for, it occurs where you have requirements for high assurance separation of information. And there are some environments where you require high assurance separation, some you don't. On this slide, I've tried to show some of the ones where separation is required, in particular where you're mixing information from different sources or different security levels might cause irretrievable damage of some sort to confidentiality. In the case where you have national secrets, there may be legal penalties for individuals and security risks for the nation if you mix these pieces of information. But there are also applications potentially in the business area. Businesses have information which is very sensitive as well. We're also concerned about assuring integrity, that is, protecting against unauthorized modifications of data that might lead to improper or unsafe system operation. And increasingly, we're concerned about availability of systems. Denial of service is a major concern today in many systems and networks. And in fact, one of my former colleagues from NRL, Kathy Meadows, is going to talk about denial of service, I believe, next week. But today, I'm going to be focusing primarily on methods for maintaining confidentiality. Now, the first part of this talk is really sort of a technology history talk. So since I've been around longer than I suspect most of the people in this room, I'll take that as a license in the event that you are not too familiar with the past to spend a little time on that. So I want to recall a time when computers were actually large beasts, okay? And I've got a picture here of one. This is a Manchester University computer, which in fact was built by the University of Manchester. Computers were things that universities fabricated at this time on occasion. And as you can see, it's a room full of components. These computers are big, they're heavy, they were expensive. They tended to deal with remote users through simple teletypes, dumb terminals, or through some sort of remote job entry arrangement. And if you wanted to add another computer to your configuration, you might very well have to consider what the air conditioning load of that machine was on the building, whether the floor supports were enough to support it, and so on. This is another machine that I included because it's a Multics machine, and Multics has a role in the history of computer security that's significant. This machine actually was still around. This one's in France. Was still around in February 1992, I guess, was the last use of it. So they're not The dinosaurs are still not too long extinct. But I want to try to set the stage for the time when this kind of work really got started, which was, I would say, in the late 60s and early 70s, when you had big machines and you had people, at least in the national security establishment, who wanted to be able to share the same machine. And some of those people would have different clearances for different levels of information. And some of them would have then there would be different classifications of information on that machine. So the question was, could this operating system, could this file system reliably separate users with different clearances and information with different classifications? And the evidence, in fact, despite the claims of operating system vendors at the time that yes, oh yes, their operating system could do this, the evidence was that, in fact, these machines were not very good at keeping secrets. And that led to some work which developed what I figured this was a Friday afternoon talk, and so we can be a little bit lighthearted, as the holy grail for this field, which for a long time was MLS, multi-level security. And that corresponds sort of to all users drinking from the same cup, but each user receiving only the information for which he or she is cleared. And that was, this was put forward in an early report known as the Anderson Report, which came out, I think, in about 72 or so, which characterized computer systems in terms of subjects and objects and accesses from subject to objects. And the idea was that any access from a subject, which might be a process or essentially a representation of a user, that access would be to an object, which would be a file, something like that, would have to be mediated by a reference validation mechanism, so-called. And that mechanism would have to provide mediation that was complete. That is, every access would have to be checked. That mechanism itself would have to be small and compact so that you could be sure it was done correctly and didn't have errors in it that would sabotage the security checking. And it would have to be self-protecting. It would have to be able to defend itself against malfunctions or attacks by software in the system. So this was the goal, okay? And it was a nice sort of intellectual goal. It was a problem that you could characterize pretty well, and people could try to build prototypes of and write papers about. And of course, like the Holy Grail, this engendered a set of what we might call crusades. And I've tried to put a timeline on this slide, which indicates some significant facts over the period from the beginning of efforts in this area up to the present day. Initially, the time before the notions of reference monitors were developed, we had what we refer to as a penetrate and patch period, in which people said, well, we have the operating system, it works, oh, we found a mistake in it, we'll fix it. And now we think this version works, and then you would find another mistake. So that led to this concept of a reference monitor, if we could only build that correctly, incorporate it in a small chunk of the system, which was the security kernel. We could make that the basis of all our systems. All the security checking would be there, and we could run untrusted programs within a domain, and they wouldn't be able to affect other domains. They couldn't leak information where it wasn't supposed to be leaked. And there was a period of trying to build prototype security kernels, and some such prototypes were in fact built in the late 70s. And there were a couple of efforts to actually commercialize those, one called the SCOMP effort, which stood for Secure Communications Processor. This was done by Honeywell at that time. Now that chain has eventually been taken over by Wang Federal Systems. There was another one that was done by Ford Aerospace at the time called Kernelized Secure Operating System. Both of these efforts really evolved into attempts to build kernelized secure versions of Unix. Okay, Unix was just beginning to make waves around this time, and securing Unix is a continuing occupation. It seems to have been a 20-year exercise that's not yet complete. The SCOMP actually led eventually to a commercial product which has descendants still on the market. It's one of the few examples that actually came out of this significant amount of effort. Once this notion of a reference validation mechanism and the idea that you'd have a system that would implement these functions was developed, the government organized something called the National Computer Security Center, which would do evaluations of systems, and it developed a book that contained evaluation criteria. And this book had an orange cover and became known as the Orange Book. It explained and documented the notion of a trusted computing base, or TCB. These original notions really came from this heritage of large-scale time-sharing systems, large mainframes, and at this time it was clear that the world was changing, and we had to start dealing with networks, we had to start dealing with databases, and so interpretations of the Orange Book for networks, there was one called the Trusted Network Interpretation that was developed. It had a red cover and was a red book. There was a Trusted Database Interpretation published as well. So there was a series of guidance being developed. There was a mechanism for evaluating systems. The whole idea of this was to get the private market to develop more secure systems. No one thought the government was going to pay for all the development. It was rather provide incentives for the private market to do it. Unfortunately, it didn't really work. Let me pick one example to explain why. Digital Equipment Corporation invested a sizable amount of effort in developing a virtual machine monitor that had a security kernel base and was built to a high level of assurance according to the Orange Book criteria. It was almost brought to market around the late 80s, but in fact DEC withdrew that before ever actually releasing it. And the real reason was, and I got this from the guy who was in charge of it, that by the time it was ready to release, it was really an old time-sharing system architecture, and time had passed it by. And so the problem was developing the high assurance components took too long, and the market was not dominated anymore by government purchases, and the time to market had become a critical factor in any computer system development. Since 1990, we've seen a different sort of development, and I'll focus on this a little bit more later. I put in roughly the time of the first firewall was about the time that DEC actually decided not to commercialize this effort. Security profiling, which is really a scheme of testing systems, came in. Tripwire worked on at Purdue to try to monitor changes to systems to see if problems have occurred, came in. The criteria development has continued, and in fact there was a federal criteria published. There were international efforts at harmonizing this. There's now something called the common criteria, but they have somewhat different structure than the original Orange Book criteria had. I just want to lay this out sort of as a historical background, I guess, for the rest of the talk. I think that's sufficient. There's a lot of other history, but I've just outlined a bit of it. In terms of searching for the Holy Grail, this MLS property for systems, I think, that in fact there was a measure of success. The Crusaders, the people who went after this, actually learned a lot about how to build MLS operating systems. DEC really showed that they could do it to a considerable degree. So some such systems were built. Some actually went through the evaluation process, which added more time onto things. Some of these products were evaluated successfully. Some were sold, but not enough to really make a commercial case for this. And in the meantime, what was going on back at the castle, so to speak, was that smaller, lighter, faster, and cheaper computers were around, and users were buying them. Okay, the old mainframe model was disappearing. People were attaching those smaller machines to networks, and mainframes were actually disappearing. A few survived, we could say, others reappeared perhaps as servers. We still have that kind of environment today. So the question was, we've all got our own machines now, do we still need MLS? Well, in fact, in the environments where these things were intended to be used, it still was a problem. If you had your own machine, it was at some security level. It was in your office. Perhaps it would allow you to get at information at that security level, but you couldn't safely connect it to other security levels. You were going to have problems because you were crossing levels. So there was still a need, really, for this kind of function. But when they tried to drink from the grail, so to speak, to use the MLS devices that had been developed, they found that, in fact, they were a little bit out of date. They were a little bit slower than the systems they could buy. And so everything seemed a little bit stale, and it wasn't really safe to connect those systems across levels and out to the internet in many cases, even if you use these MLS components. So, but we had these components out there. So we tried to use them as best we could, and in fact some of them are still being used. But the way that they've been used primarily has been in the form of things called guards, okay? And a guard in this context is typically a device that's designed to sit between two security levels and try to filter information that's coming out of the higher security level and going down to the lower security level, try to see that you can be sure that in fact the information that's going down is okay to send down. That's not the way these systems were designed. That's not the function these systems were designed to support, these operating systems. They were designed to be very sure that two domains were in fact isolated when you thought they were isolated. And the whole function of this kind of device is to make a connection between domains. Now, it's fine that you've got a strong operating system and you can be sure that there's only a connection where you think there is, but you're basically faced with buying a machine that was a little out of date, a little underpowered, and a little more expensive than one with a somewhat weaker operating system. And what you were doing in the end was funneling information across levels anyway. So that's not been entirely successful. Now what I've drawn on this slide is a characterization of some of the architectures that we have in systems today throughout the military, I would say. We typically have systems structured into layers. We have networks that operate basically at a single security level. And here I've shown 3 such levels. And we have connections typically, at least in some cases, across levels. And that can be a problem because it's very hard to determine what's a safe connection across levels. So I've put a guard in here between the secret level and the internet, so to speak. And we may find people on the secret system who want, for example, to send email to people who are on the internet. If they're going to do that in this context, they are likely to wind up sending that email through a guard, which has to try to figure out that this email is actually not some kind of classified message, and then allow it through or not. As you can imagine, that's a very difficult property to determine just by looking at the data if you don't have some other information. And so what we're really faced with is a difficult certification problem. The person who's tasked with saying it's okay to operate this system, the risk isn't too high, has to somehow believe that this guard is capable of something which is really a very difficult function. And often you'll involve a human in the loop to actually assist that. But even for a human, it's a boring and repetitive task. It may be difficult to perform correctly for a long time. Another kind of device that's sometimes used across networks I've shown here is what's called an inline network encryptor. And the idea here is you may lack connectivity between 2 parts of one network that's at a given security level, but you have connectivity at a different security level, in this case a lower one. And so it may be all right to send data across using the lower level network if you encrypt it before sending it down. But I would point out that what's going to happen in this case is you will encrypt the data, but the lower level network still has to route that data somehow. And so the packet headers that are used for routing down here are probably going to have to stay in the clear, otherwise you won't be able to determine where it's supposed to come back out and go back up. We'll come back to that a little bit later. Okay, so that's where we've gotten to. It hasn't been a great success. You know, I've been in the field a long time. I've seen a lot of things developed, a lot of research done. We've learned a lot. But in terms of getting solutions actually into use, it's been very difficult. And so I think we need to go back and look at the system architecture questions. You know, what kind of solutions actually are going to be effective? And this slide is talking to that point. I think that we have to have a system architecture that permits a flexible use of commercial off-the-shelf technology, including database management systems, for example. It needs to be able to enforce what we call mandatory security policy. That means the business about classifications and clearances, okay? It has to be able to deal with the systems that we have, because now there's a very large installed base, not just in the private sector, but also in the public sector, and you can't just throw that out. You've got to be able to work with it and replace it over time. Further, the architecture's got to be able to be understood by certifiers. It has to be something you can explain to people as to why it's secure. In fact, it can't require a sophisticated logician with a PhD in order to decide that this thing actually is an acceptable configuration. And it has to permit some degree of local autonomy, because you've got different applications, different environments. People will need to tailor their systems. So my argument, which I'll be trying to persuade you of for a large part of the rest of the talk, is that we can approach this best perhaps by having high assurance security policy enforcement assigned to separate simple components, rather than trying to say we're going to have an MLS operating system running all over the place. And then there has been advance, I would say, in the ability of commercial products to support security policies, not, I think, up to the point where we want to trust them with high assurance enforcement, but enforcement, for example, of discretionary security policies within a given security level may be within the domain of what's practical for commercial technology. So if you can create an environment where the commercial threat model is appropriate, then it may be okay to rely on commercial products for enforcement of security policies. And let me say a little more about what I mean by commercial threat model. In the commercial world, you have, not only pieces of hardware to enforce things, you have a police force, you have courts. If someone does something bad to you, you have recourse to other mechanisms, ways of getting restitution, other than just dealing with things within the system. And that's not always true in a military environment. You can't decide after somebody bombs you that you're going to take them to court necessarily, or if someone attacks you in wartime, that's a different situation. So you have a different threat environment and different remedies available, and you have to take that into account when you're developing systems. Okay, so now this is the gadgets and cheap tricks department. Okay, the question is, could we perhaps get the kinds of functions we wanted to have out of multi-level secure operating systems running on people's desktops could we get those functions without requiring a high assurance operating system? And I'm going to claim that to a surprising degree you can. And some of the components that I'm going to talk about are shown in this slide. I'm not going to talk about all of them at this point, but I'll just point to them briefly. This symbology is referring to a device that we call the pump, which is a one-way upward flow device, but provides an acknowledgement downward as well. This is actually a combination of two things. The diode symbol is indicating a physically one-way upward flow. No acknowledgements go back, nothing goes back. And this is indicating a switch, trusted switch, which is attached to the keyboard in this case. This combination of the trusted switch and the one-way upward flow is going to provide us with something which is very close to a multi-level secure client. And the pump, in combination with a database replication scheme, can provide us something that's very close to a multi-level server, database server function. And this is being called multiple single levels in some cases, or MSL instead of MLS, or in some cases single level at a time, or SLAT today. Let me focus in on the client function, and this is actually the schematic representation again of the keyboard switch and the physically one-way upward link between two networks. Now, this approach was actually developed in Australia at a defense laboratory there, and was originated by a guy named Mark Anderson. And it was based initially on the observation that if we had an X Windows environment, we could basically, perhaps we could find a way to have multiple windows on the workstation where one window would represent what was going on the high side, and another one represent what was going on the low side. The low side window really just being representation of the display being reflected upwards from the low side. Now the trick here is this. I have a single workstation. It's got a processor with it. The processor is attached to the high network, so that's a sensitive processor, okay? The keyboard, however, has a switch, and the keyboard keystrokes can be switched either to a low network or to the high network. If the keyboard switched to the high network, that's fine. I can access information on the high network. I can generate results. The processor can paint the high screen, the high window. All works normally. If I want to get information from the low side, I switch the switch to the low network, and now whatever I do, those keystrokes will go to some shared Unix server out here. The results, if I start up a browser, for example, on that server, and I start browsing the internet, say, or whatever low network this is, the results from that browsing are going to be represented. The results that would be shown on the screen will come across as display X events, okay? And those events are sent up via this one-way link to the high network. The browser's not running on the high side. The browser's running down here. But it's just as though we have basically a remote version of the display being reflected up. And now I can see that. So I can sit in my office with one machine, which is what a lot of people desire, and I can actually see what's going on the low network and on the high network as well. If I want to go back to the high side, I switch the keyboard. But at no time have I actually sent any information down. If you look at this picture, there's no path, no physical path that would allow information to flow from the high side to the low side. So the certification of this, in theory, should be a lot simpler, right? I just have to be sure that this switch really works the way it's supposed to, and this diode really works the way it's supposed to. The name of this device is Starlight Interactive Link. It's actually in commercial development now. And I think I've covered most of these other points. I guess cut and paste upwards, in fact, can be supported because the cut buffer can also be reflected upwards over this link. So I can actually have upwards communication between those two windows, which is another thing that was desired of an MLS operating system. It requires one processor per person using this scheme, but the low processor can be shared across many users. The commercial development is actually targeted at an evaluation level. This is under the common criteria now, I think, or maybe the immediate predecessor of that, but it's, this is a high level of assurance. It's E6. Higher numbers are higher assurance in this scheme. This slide shows an alternative approach, which is even simpler, I would say, maybe a little bit less elegant. This depends on something referred to as a server switch, and this is a piece of technology that was developed entirely independent of security considerations. It was basically designed if you have a lot of servers or routers, say, in a closet, and you want to just have one monitor and one keyboard. This is a switch that will allow that monitor and that keyboard to be switched to the outputs of any of those servers. Well, that gives you another way of dealing with two levels of system. I can basically just switch my switches to the low side, and now both the monitor and the keyboard are switched to a low processor. If I switch to the high side, they're switched to the high processor, and I can have one monitor and one keyboard on my desk. I don't have any way of transferring information from the low level to the high level unless I add in an additional component, and that's, again, this physically one-way device. I've added also, this is a representation of a buffer, because if you have a physically one-way connection, what this typically would be is a fiber optic link with the transmitter and receiver oriented so that there's no transmission downwards. If you do that, you don't have any way of knowing whether or not the buffer on the high side is full when you send data up there. And so you need to have an amply sized buffer, and you may need some low-sized throttling mechanism that you can adjust with user feedback, perhaps, if you find you're losing data. So if you have a server switch represented here and the one-way upward link, you actually can support sending files upward, and you can give a user the ability to either see the low activity or the high activity. The downside of this configuration, perhaps, is that you can't subdivide this. You can't really see a window at low and high unless you get into doing some more sophisticated stuff with the video. And you also require two separate processors per seat. Okay, I can't share the processor in this case. But this is, in fact, a solution that has been used. Now I want to talk about a piece of technology that was developed, in fact, at the Naval Research Laboratory, and is, in fact, in the hardware prototype stage right now. We've had software prototypes for some time demonstrating the function of this. The idea of this device was to avoid that problem with the buffer that I just alluded to. Okay, if we actually want to have close synchronization of two systems, a database at low and a database at high, we really need that acknowledgement to provide reliable transmission. We need to provide reliable synchronization between the two levels. You can't just have a buffer there that is more or less free running. The problem is that allowing the acknowledgement is a downward flow of information, and if you're in a high assurance environment, that acknowledgement itself is a source of concern, because if you have, as we do have, in fact, basically untrusted software running on both of these networks, it's possible that malicious software running at the high side could try to use that acknowledgement to signal information downward. So the pump has been designed so that the acknowledgement, the timing of that acknowledgement is randomized, it's fuzzed, I've said here, so that in fact the amount of information that can be transmitted that way is extremely limited. But the acknowledgement that is given when the low side sends some information to the pump, the amount of information transmitted is, when the pump receives data, the acknowledgement represents a commitment on the part of the pump to eventually transfer that data to the high side. And the way that the acknowledgements are in fact timed, it's designed so that if the buffer starts to fill up, if the low side is sending more data than the high side can receive, gradually the time between those acknowledgements will be spread out. And there's also some auditing done, so if you do really have a lot of overruns, somebody will be alerted to that fact. Okay, this is actually a bit of a shift of gears because this doesn't actually involve crossing security levels, this piece of technology that I want to talk about. This is about protecting internet browsing from traffic analysis. Okay, it's something else that is of some interest to people who don't want other people to know what they're looking at. Okay, it's worth initially describing two parts of this, I think, two parts of this problem. A lot of people are familiar with sort of anonymization techniques, I think, in which the initiator of a reference is trying to hide their identity from the destination, okay? And that I'll refer to as anonymous communication. So I could send a message to you and you wouldn't know where it came from. This technology isn't so much concerned with that, but it's concerned with the problem that almost anything you send over the internet now is not only visible to both ends, but visible to all the routers in between, okay, unless you take measures to encrypt it. Every router that is on the path of the communication is going to be able to read the communication and whatever's in it. What's more, it not only, even if you encrypt it, okay, it's possible to trace the flow of the packet. The headers on the packets will tell where the packet is destined for. So I may not be able to read the contents of the packet, but I may know very well that in fact company A is talking to company B. And that may in fact give me a lot of information. So the current state of affairs is quite open. And the question is, could we add technology on top of that that would provide a way of having protected web browsing? And the scheme was developed by David Goldschlag and Paul Syverson and Michael Reed at the Naval Research Lab. This particular scheme is called onion routing because it involves creating a layered data structure which is wrapped up with several levels of encryption. It's a connection-based protocol, and it depends on having onion routing nodes. And these are application-level routers. They're not internet-level routers. Okay, these right on top of the internet. If I want to make a reference to a particular, I want to communicate with a particular destination, the initiator creates this layered data structure. Each of these onion routers has a public key and a private key, and the public keys are used to encrypt. Well, you choose a path and then you encrypt it in layers using the public keys of each of the elements of the path to encrypt that data structure. The onion that's created is then sent to the first node, which can unwrap the outer layer of the onion, determine who's next, send the onion that far. That node now removes its layer, sends it on to the next node, which removes its layer, and so on. Each one of these nodes in the path can tell where its data came from and where the next hop is, but it can't tell what the ultimate destination is or what the ultimate source was. Except, of course, the first node created the whole thing. When the data pops out of the last node in the path, it's in the clear. Okay, so the data is clear at this point. The server at the far end doesn't have to know anything about onion routing. It just sees this data come in. It doesn't know where it came from except that it came from the last node in the path, and it sends it back there if it has a response. Okay, so the response goes back along the same path, but in this case a layer is added each time to the data until it emerges at this end, and now this end has to do all the unwrapping. This may seem like a lot of encryption, but in fact it's no more encryption operations than you would have if you did link encryption, because if you have link encryption, each time you go across a link you got to encrypt and then you decrypt at the far end. So this number of encryption operations is basically the same. NRL in fact built an alpha level prototype of this thing, which is in fact available for use at the address indicated here. Now, as I said, this is designed, the technology was really developed to protect against traffic analysis within the network. However, we do also have two proxies with the system, one of which does not try to anonymize the data stream, that is to hide the identity of the initiator from the destination. We do have another proxy that does include some measures for anonymizing the data stream, so it'll strip out obvious things that would identify the source. But that's actually a very hard problem in itself, and other people have focused efforts on that, and it would be, the idea was that we would be able to take advantage of other people's work in that respect. This is just going through what I've just described, the data movement. Once you have the connection open, then the data flows through. The only real significant difference here is once data is flowing, you don't use the public key algorithms because they're much more computationally expensive. What you've done when you set up the connection is distribute a set of symmetric keys, which you use for encrypting the data. So again, the initial node has got to encrypt the data with all the keys of each of the nodes in the path, and then each one removes a layer, and again, data coming back gets built up the same way, but again, this time you're using symmetric encryption. Okay, so that's a quick overview of onion routing in general. This is just to emphasize the point that in fact onion routers are not internet routers. Okay, the path from one onion router to the next may traverse many internet routers. That's no problem. The packet headers there are definitely going to say that, you know, this packet is going from A to C, but that's okay. It isn't really going to reveal anything to an observer that you're trying to protect. The current state of this is, in fact, I guess there are two things relevant. There's a beta version of this that's been under development for over a year now. The beta version has, well, a couple of issues occur with this approach. One is that connections can break, okay, between onion routers. In general, we maintain long-term connections among onion routers in the network, and we needed a scheme for topology information maintenance so that we could pass information about the current state of the network back to the creator of an onion. So the beta version has a good deal of effort put into streamlining things and adding functions for topology maintenance, and also for flexible configurations. So you may want to run an onion router, for example, on your firewall and on the firewall of someone you communicate with a lot. You may want to run it on a client behind the firewall. There's a number of possible ways to configure it. There's also been a commercial development in Canada that's based on very similar technology by a company called Zero Knowledge Systems. A difference is that their version uses UDP packets. It doesn't set up connections in the same way, but it's otherwise very similar, and I think draws on this technology. Okay, so back to my argument about multi-level security. On this slide, I've just shown some icons that I've been using to represent the components that we've talked about, because I think if you're going to actually do system architectures this way, you need useful little symbols to represent things with. I'm not going to harp on these again, except to mention this one. This is showing a filtering downgrader, and this is really the sort of function that guards are intended to provide. That is, I'm going between two levels of network, two networks at different levels, and I want to do some kind of filtering. It would be nice to be able to configure systems so you didn't need that, but as far as I can tell, we're going to need that for the indefinite future. The trick is to configure the system architecture so you do that as little as possible, because you always encounter some risk in doing that. Okay, so back to the idea of MLS service without MLS operating systems. What I'm showing now is a secret network and a secret but sensitive but unclassified network. this is sort of the full-up configuration in which I've got a user at single workstation. He's got access to both networks. He can have a window displaying information from the high side. He can browse the high network. Everything will be displayed there. He can browse the low network by flicking this switch. Everything will be displayed there. He can actually do protected web browsing using the onion routing facility that's shown here. You can have database updates coming into this database that will be reflected automatically up to this one, which will contain both the lower level information and the higher level information replicated from down there. Now, one of the issues for our military forces these days is we're always fighting as part of some coalition. And you've seen that, I think, quite vividly in the last few years. And so it's fine to have systems that work just, that we can take care of at home, but you've got to have systems that will work with other countries. And that really means you're dealing with some coalition, and usually you're not going to be willing to release everything to the coalition that you have at home. In many cases, you're obligated not to do that. So one way of handling that problem with this kind of technology is to say, okay, we'll establish a coalition network, and we'll put some systems out there, and our partners can add data to that network as they wish to. And in this case, now I can what I still want is to be able to have one workstation, see the coalition information, also see my national information. Okay, and this is just to try to show that we can support this with this kind of architecture and these components. In coalitions, you've not usually got just two people, but you have many, and this is just trying to show that we can actually generalize this, because typically different nations aren't going to agree. Their local national information is going to be sensitive to them. What's nice about this scheme is that each country can have the ability to update the coalition database with whatever information they're willing to release. Those updates from the coalition database can be propagated back to the national databases, so you can have consistent information coming from the coalition going to nation A over here, and from the coalition going to nation B over here, and each country can have consistent information augmented with its national information. And this can be critical when you're in a complicated operation, that people have up-to-date and synchronized information. This is really about where we are with this kind of work. Both the pump and Starlight are really still not deployable technologies. They're at the prototype and the early commercial development stage. But I think that rather than trying to build, the holy grail, okay, the perfect operating system that will be deployable everywhere and will solve all our problems, I think the real security that we've seen deployed in the last 10 years has come from, in fact, add-on security. It's heresy for somebody perhaps of my generation to say that, in fact, security is an add-on property. We always say you've got to consider security from the beginning. But it's perhaps worth thinking about the successes that there have been in security. And one of the main ones I would think everyone would have to agree is the use of cryptography. And the reason that I think that cryptography has succeeded in many cases is it's an add-on property. You can take a link, you can add a couple of cryptos, and now it's secure. If we can find the right kinds of components and the right kind of properties where we can get that kind of behavior out of our legacy and our off-the-shelf commercial systems, I think we'll have a much better chance of having secure architectures. So I don't think that, we're not by any means done with this process, but I think this is a direction in which we might want to try to think for now. And we have to think about interesting components, and I think we've got a couple of examples out there now, how to structure systems that can use those components, get the job done that needs to be done. It's not the case that we can, in general, tell people, well, you're going to lose 10% of the function, but it's more secure. If you tell that to most people, they'll say, well, I'm willing to take the risk. Give me the rest of the function, and I don't need the security. We need to find ways that will provide all the function and yet be more secure. I think in the future we're going to see more integration of data management systems, more pressure for security at low cost, and for architectures that can incorporate commercial and legacy systems. I think if we have data management architectures that will rely on simple high assurance components and commercial off-the-shelf products where they're appropriate, where their threat model applies, will have a better chance for meeting future requirements. I think the last slide is just a few references for the particular technologies that I've talked about. So I guess at this point I'd like to open it up for any questions you may have. As I say, I'm happy to be here, and I'm happy to answer any questions you might have. Yes?
Yeah. With the coalition database that you were dealing with, I guess the focus really was on maintaining the separation between the two levels of confidentiality.
Right.
But what sort of stuff has been looked at in terms of trust and veracity of the information supplied by other people into that public database?
Well, the question is how do you assure the integrity of updates that come into the coalition database? It's a data quality question. Is that what I'm?
Okay. Versus saying someone intentionally putting in less accurate information into the publicly, not the publicly, but the coalition database, where you have better information possibly contained in your database, or deliberately entering misinformation into the coalition database. I mean, how is that handled with the network pump?
The pump is not really going to handle those problems, but let me clarify one thing. As far as entering bogus information, I don't have you could try to do I guess you can authenticate the guys putting it in, and you could tag the data somehow as to where it came from, and then if you discover it's in fact wrong, try to trace back. The pump is basically, really just a mechanism for communicating across security levels. In general, the way that in the prototypes that we've done of this kind of operation, you would not simply take the coalition database, a record from that database, and replicate it into your own database. You'd probably replicate that into you'd mark that in effect, so you wouldn't be modifying your data based on a coalition update. You'd actually you might have either distinguished fields, distinguished records in the database for the two different entries. So merging them actually is a significant issue. Any questions? No?
The rainbow books that were basically out by the government, the orange, brown, red.
Right.
How off were they when they started creating these books? In comparison to where the technology is today? I mean, has it evolved in a direction that's going to be more, I don't know, acceptable to what you were trying to accomplish, or do you think the standards are going to take us to a different level?
Well, there was actually considerable discussion at the time that those, let me just refer primarily to the Trusted Computer System Evaluation Criteria, which is the orange book from which the others really derive. The way that book was structured, and it's still actually, I think, not a bad thing for people to read, because it's not, in a sense, I think the concepts that it incorporates are in fact still valid. That is, if you want to build an operating system that's able to separate domains, you could follow that guidance, and it would be appropriate. The way that the guidance was organized, however, it defined levels of systems in terms of both functions and assurance. Okay, so if I was going to build a B2 system, I have to include the following functions and the following sorts of assurance. And assurance in this case meant a certain kind of documentation, a certain degree of testing, a certain process. And those were, particularly the documentation, was extremely cumbersome for people to produce. And that added a lot of time and cost to projects. The way that the criteria have evolved over time is to actually split those two kinds of requirements. So if you're developing a secure product today, or a product that wants to provide some security functions, and you want to have it evaluated by the common criteria, you typically have to write something called a protection profile, which specifies what functions it is you've got, and then you choose a level of assurance yourself. And so there's more flexibility for the developer to develop a product that they think meets market needs, rather than meeting a pre-specified set of functions. It puts more of a challenge on the system integrator to make a system out of components that may or may not fit together so neatly. The idea behind the Orange Book was, it's too much to expect people to be able to make sensible choices on those things. Here's the things that we think make sense together. There's a little bit more flexibility now and a little bit more risk for the system engineer, perhaps. Does that answer your question? Anything else? Yeah.
What's the nature of the switch itself? Hardware, software on the keyboard in Starlight? What is that?
Starlight Interactive Link, the switch, actually, the current configuration is actually, seems to me, intellectually much larger than it needs to be. It's basically a pizza box that would sit, on top of your existing pizza box. And you basically, there is some processing in that box, okay? There are some, there's a few issues that I've glossed over a little bit here in terms of, they're not security issues, but there are functionality issues that can be complicated because since you've got this one-way upward link, you have to have proxies. The protocols in many cases you're dealing with are really two-way protocols to some extent. And so you have to write proxies at the high side and the low side that dummy up the side that isn't really there. And if there's actual communication that went on, the color map changed or something like that, you've got to find sensible ways to deal with those problems, and that's been an engineering problem in that device. So I guess the switch is, it's not a simple relay. It's not as simple as that. There's a bit of software to evaluate. I think we're going to continue to have devices where there's a need for some degree of high assurance software. The trick is to really minimize that as much as you can because it's very expensive to produce that kind of software.
And so if you are not an authorized person, you simply don't have that additional pizza box, right?
Right. I mean, the assumption is that if you're sitting at a workstation that has that box has physical access to both networks. So if you're in a room with physical access to that network, you should be authorized for it. But you might have the low network, of course, could extend anywhere if it's the internet. Any other questions? If not, thank you very much.
Thank you.